That correction, 1926, won him the Nobel Prize in the early 1950s. Axiom 4, and we're almost done. There are only 5. We're making great progress. Axiom 4 says the probability with which a measurement by an observer of an observable A, probability with which a measurement by an observer of observable A yields an eigenvalue lambda A is given by the Born rule. That's the Born rule, named after Max Born, grandfather of Olivia Newton-John. But no one who's under 40 has any idea what I'm talking about. Is there anyone under 40 who knows what I mean by that? Wow. Born rule. One of the lesser known Jason Bourne movies. What is the Born rule? It says that probability, the probability, that's P, probability, with which you will obtain the result lambda A is given by, take the system's quantum state represented by the density matrix, you multiply by a certain operator, P hat, subscript A. What is that operator? It is the operator that projects onto the eigenspace for that eigenvalue lambda A. So we imagine you've got an eigenvector corresponds to A. There could be more than one. They all have the same lambda A eigenvalue. Those vectors span a little subspace of the Hilbert space. And this is an operator that just takes whatever your thing is and projects it down onto that subspace. And then you take the trace. Trace of a product of matrices is the sum of the diagonal entries. Multiply these two matrices together, we get an n by n, and we just sum the diagonal entries. And this is called the Born rule. It roughly resembles, if you just sort of take your glasses off and kind of squint a little bit, it kind of looks a little bit like we're summing, that's the trace, over a certain projected set of probabilities to get a net probability. That's what it's supposed to sort of evoke. Now, this is not the most well-known version of the Born rule. If the projector happens to be rank 1, then it is simply an outer product of this form. It is also an outer product if rank 1. And if the quantum state itself is also rank 1 and is expressible as an outer product as well, if they're both rank 1, then this formula simplifies further. And it just looks like you take the inner product, this is the bracket of A with psi, and you take the modulus and you square it. And it turns out this formula is just what this formula reduces to. And this says we get probabilities for measurement outcomes in quantum mechanics. We take our quantum state, we take the eigenvector associated with the eigenvalue of the probability that the eigenvalue of the observable that we're measuring. We take their inner product, so row vector times column vector gives you a number. The number is in general a complex number. We mod square it, that means we take its absolute value as a complex number and we square that, and the result is the probability. And this rule in its most primordial form was written down in 1926 by Max Born. And the story behind this was Max Born originally did not include the absolute value squaring. And then after the paper had gone through peer review and was ready to be published, he had second thoughts, and so he requested a modification which became a footnote. Note added in proof on further reflection. It is not this, but the modification is that is the actual probability. That correction, 1926, won him the Nobel Prize in the early 1950s. It was a Nobel Prize winning correction. Note added in proof. Okay. This is the Born rule, and this gives us our probabilities. We now have probabilities. We can now say what is the probability with which we'll get a certain result. And then as soon as you have done that measurement and gotten that result, one final thing happens, and this is the famous collapse of the wave function, the collapse of the quantum state.